This video is going to cover the 6-4 warm-up and then the 6-5 notes. If you haven't already allowed about 5 minutes for everybody to work on this warm-up, if you'll pause the video and then replay it once that 5 minutes has passed and everybody's ready to go through the answers. Okay, so in 6-4, we talked about dot product, angle between, and orthogonal. The dot product is found by multiplying the first two terms in the component forms of these vectors, so 7 times 2, and then adding it to the product of the second two terms, so -3 and 8. From there I get 14 and a -24 or -10. Dot product, again, would always be that one number. To find the angle between two vectors, we used the equation that is the cosine of theta would equal the dot product of the two angles over the product of their magnitudes. So if I want to find the dot product, I did it in the first part. That's -10. That's going to be my numerator. And then the magnitude of u would be the square root of 7 squared plus -3 squared, 49 plus 9, which is the square root of 58. And then the magnitude of v, so this is u, the magnitude of v would be the square root of 2 squared plus 8 squared, or the square root of 4 plus 64, which is the square root of 68. So I don't need to simplify these because I'm going to let the calculator do that work for me. I'm going to do cosine -1, and then it's going to open the parentheses, and I'm going to type that all in, making sure that both 58 and 68 stay underneath the square root. So cosine -1 of -10 divided by square root of 58 times 68. And I get that theta is 99 point, we're going to round this to 1 decimal place, or 0.2. And then remember, we talked about these are easier to check because you can graph these two. So again, it won't be 100% accurate, but you can kind of like eyeball it. If my component form is -3, I'm going to go 1, 2, 3, 4, 5, 6, 7 down, 1, 2, 3. That would be the first vector. And then the second one, 2, 8, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, all the way up here. And this definitely appears to be about 99 degrees, which is what we found, so at least we know we're on the right track. To determine if they're orthogonal, we look at the dot product or the slopes of these two. If the dot product is 1, then I know that this is orthogonal. If it's not, which in this case it's not, I know this is not orthogonal. The other thing it could be is parallel. So for those, remember we take these and we look at the slopes of them. So I would do -3 over 7 and then 8 over 2. If they are the same, then they're parallel. If they're opposite reciprocals, then they're perpendicular, which means they're orthogonal. Or the dot product would be 1. In either case, this time it is not. Okay, so the last section we're going to cover before your test is Chapter 6, Section 5, which is called the trigonometric form of a complex number. So we're going to combine what we know about complex numbers into a little bit of this content that we've been talking about. The first thing we're going to do is determine how to plot an imaginary number, a complex number, on a complex coordinate grid. So this is exactly like your X, Y coordinate grid, except the real axis is going to be take over the place of the x-axis, and the imaginary axis is the y-axis. So if I have a number like 3 plus 2i, the 3 is the real part. I would go over to 3. 2i is the imaginary part, and I would plot that point. So again, real axis is your x-axis, imaginary is your y. If you remember standard form, the I always came last, so it should make sense that it would be x, y because the y comes last. So hopefully that helps you remember which axis is which. The absolute value of a complex number is found by, if my complex number is a plus bi, the a is the real part that's by itself. The b is what's in front of the I, so we don't include the I. And the absolute value is defined as the distance between that origin and that point. This should sound familiar because that's also the magnitude of a vector from the origin to the end point or the terminal point of that vector. So we find it by doing the magnitude, or the square root of a squared plus b squared. So absolute value is equal to the distance is equal to the magnitude. Here's an example. It says plot the complex number and then find the absolute value. So if I start with A, I'm going to plot -3, 6 plus 6i. -3 moves back 3, and then 6i is up 1, 2, 3, 4, 5, 6. My point would be there. The difference between this and what we were doing in the last couple sections is this is not a vector. This is simply a point, so it stays just like that. But the absolute value is found the same way as we were doing the magnitude. So it would be the absolute value of -3 squared plus, I ignored the I and just take the 6. And I'd get 9 plus 36, or the square root of 45, which breaks down to 5 and 9, 3 and 3, and this becomes 3 root 5. B says 2 minus 4i, so I'm going to move to the right 2 and then down 4 and plot my point. That's B. This one was A. And this would be the absolute value would be 2 squared plus a -4 squared. But notice these signs don't really matter because when I square them, they're always going to go back positive. I get square root of 20, 2 and 10, 2 and 5, or 2 root 5. Next up is the trig form of a complex number. So the trigonometric form of the complex number z equals a plus bi is given by z equals r times the cosine of theta plus I times the sine of theta. Now I can go in the front here in front of the sign, or it can go at the end. It would also be the same thing to say r cosine theta plus sine theta I. Putting the I to the end change nothing about this except that we are not finding the sine of I. You're just finding the sine of theta, which is why it normally bumps it to the front. So A would be r times the cosine of theta, and B would be r times the sine of theta. R is again square root of a squared plus b squared because r is just like the radius. So if I had plotted a point, something like 2 or 3, 2i, something like that, this distance here, which is also known as the absolute value, it's like the magnitude, it's the distance between the origin and that point, it's also the radius. All of those are found the exact same way. So I need to find r by doing a squared plus b squared square rooted. And I also need to know what theta is. So I'm plugging in a value here, and then this value would also get plugged in. And if you remember your trig functions, if I close this in as a triangle and I wanted to find the angle here being theta, this is my A value, this is my B value. So the tangent of theta would be B over A, and if I wanted to find that angle, I would do the tangent -1 of B over A, and that's going to give me theta. So R is the square root of A squared plus B squared, and theta is going to be found by doing the tangent -1 of B over A. This is just some vocab here. It says R is the modulus of Z, and theta is called the argument of Z. You won't be tested on that, but your book might refer to it just in case you see it pop up. Now the last part there says use the value of tangent to find the reference angle and the location of the original point to find the quadrant. So remember, if I'm using this unit circle based and I get something like the tangent of theta is root 3. Again, we go back to unit circle. Hopefully you remember your tangents. At 0, tan is 0. At pi over 2, it's undefined. At pi over 6, it's root 3 over 3 because it takes 2, 3 to make 6. At pi over 4, it's 1. At pi over 3, it's root 3. So that will give you the reference angle. But then if my coordinate point is, let's just say it's 4i. So I went right, 1, 2, 3, 4. I went up, 1, 2, 3, 4. There's my triangle. If they're both positive, I know I'm in quadrant 1. And in quadrant 1, the pi over 4 is pi over 4. But if I said negative 4 plus 4i, now I'm going 1, 2, 3, 4, up 1, 2, 3, 4. Now I know that that reference angle, because the tangent would still be negative 1, so it could be down here or it could be here. But because I've moved left and up, I know it's quadrant 2. And the over 4 in quadrant 2 would be 3 pi over 4. So for each answer of tangent, there are 2 answers that apply. The one in the first and the third quadrant for the positive tangents, and the one in the second and the fourth quadrant for the negative tangents. But the original location of your point, because that's going to be given to you, is how you determine which of those 2 you're going to use. Okay, let's see an example of that. Hopefully that will make more sense. Example 2 says, write the complex number in trig form. So here's the 3i. It actually has no a, so it would be 0 plus 3i if I wanted the a. That means I'm not moving left or right at all, but I'm going up 1, 2, 3, and there's my coordinate point. This time, I need to find my r, which would be the square root of 0 squared plus 3 squared, square root of 0 plus 9, square root of 9, which is 3. That's the r. And I need to find theta. Tangent of theta is going to be b, which is 3 over a, undefined. And tangent is undefined, 2 locations, pi over 2 and 3 pi over 2. But this is clearly here at the top of my circle, which would be pi over 2. So now I have both r and theta. And I would write this as r times the cosine of theta plus I sine theta, or 3 times the cosine of pi over 2 plus I sine pi over 2. And you'll leave it just like that. WebAssign may require these little parentheses around your angles, but on an open-ended test like is what you'll have, you can leave it the way that it is, as long as that I is bumped to the front so that you're not taking the sign of I. Example 3 says write the complex number in trig form, and my coordinate or my complex number is -2 minus 2i. So I'm going to move left 2 and down 2. That tells me it's going to be in the third quadrant. My r is the square root of -2 squared plus -2 squared. Square root of 4 plus 4, which is the square root of 8, simplifies to 2 root 2. That's r. And then the tangent of theta is b, which is -2, over a, which is -2. Tangent of theta is 1. So remember before we said there's 2 answers for tangent being -1. It's at pi over 4, and it's also at 5 pi over 4. Because I know this is happening in the third quadrant, I know theta is 5 pi over 4. So I know z equals the radius, 2 root 2, times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. So with extra time, these are actually easily checked if you know your unit circle well, which hopefully you do, because otherwise you can't get to the answer to begin with. But if I know the so if I go back to that 5 pi over 4, I know the coordinate point here is negative root 2 over 2 and negative root 2 over 2. So if I take 2 root 2 and I multiply the cosine there, is going to be negative root 2 over 2. Plus I times the sine there is also negative root 2 over 2. And then I distribute 2 root 2 to each of these. I'd get negative 2 root 2 times root 2 over 2. The 2's are going to cancel. And root 2 times root 2 is 2. So it's negative 2. Plus I multiply these together. 2 root 2 times negative root 2 over 2. It's a lot of 2's. 2's are going to cancel. Root 2 times root 2 is 2. And I get negative 2. That's negative minus I times 2, or negative 2 minus 2i, which is the same as the original question. So all of these can be checked by working backwards to double check your answers, as long as you know those unit circle angles. Okay, that wraps up not only 6-5, but also everything that's going to be on your test. So you're going to take this time to submit your notes, the warm-up and the notes in one file, and then use the remaining time to work on your homework. Enjoy your weekend, and I will see everybody on Tuesday.